Oh, I don't have good opinions about how to make movies or TV shows.
Oh, so that's just me then. Yeah.
I mean, I have opinions. I just recognize that they're not good.
I recognize that yours aren't good either. We're agreeing on that point.
Oh, good. All right. I long ago realized that I do not have an eye for developing film or TV shows, and that's fine. Like, not everybody's good at everything. So, lean into my strengths, which is drinking coffee and rambling.
And you're all out of coffee.
Hello, alleged human, and welcome to the Chaos Lever podcast. My name is Ned, and I'm definitely not a robot or a bobblehead. I am a real human person who nods their head on purpose and is not forced to by a spring that's attached to my neck. With me is Chris, who is also here. Hi, Chris.
You have proven nothing. You could very easily be a robobblehead.
A robobblehead? Trademark that immediately.
Yeah, that's going on t-shirts. Ironically, not on bobbleheads.
Well, there's a question for listeners out there. Do you want Chaos Lever t-shirts? And if so, what should they say? I have no idea.
I'm leading with, of course, Ned is wrong.
That's just generally true all the time. We have a new website, pod.chaoslever.com. Apparently, you can leave comments and voicemails. So if you have a strong opinion about a shirt or some other piece of merch, I guess let us know. We might even make it. Maybe.
We'll see.
Yeah. Don't get your hopes up. Oh, good. I'm glad we've struck an adversarial tone with the 4 people who are listening to this podcast.
Who are you and how dare you?
And Mom, I'll be there at 2 this weekend, not 3.
It's so cute you think your parents listen.
Oh, no, I know better. They gave up on listening to my crap after my whole parody death metal band phase.
That's fair.
Yeah, it was best for everyone. That they even tried, I appreciate. Let's talk about something else.
Yeah, let's do that.
Okay.
It occurred to me that we both have and haven't talked about quantum computing in a while.
There it is. Yeah, gonna be a lot of that, huh? All right.
So this all came to me rather quickly, as a matter of fact. In the run-up to it being my turn to write the main for this week, 2 things occurred to me almost simultaneously. One, it was already Thursday evening and I hadn't done shit, which felt like a problem.
Yeah.
And 2, we actually haven't talked about quantum in a while.
Yeah, I didn't look it up. Did you look it up?
I meant to look it up, and I didn't look it up.
Well, now we know what goes on the shirt.
I mean, I don't even think we've done the quantum joke in at least 10 episodes.
Yeah, that has fallen by the wayside.
And hasn't.
Oh, that was no good.
Anyway, theoretically, now that we've taken care of that, we could probably just shut it down and save the nice people 25 minutes. And we don't even have to mention AI.
Ooh, could we get through a whole episode without mentioning AI or Elon Musk?
We'll see.
One very angry reviewer would like us to stop dunking on Musk, to which I say, that's really what Elon does to himself. We're just here to observe.
It is not our fault that he puts his office in the basement under the hoop.
Precisely. Anyway.
Anyway. We could go on. And we will.
Here's another shirt.
So let's start with the basics. Point 0. How do quantum computers, work?
Okay. Mm-hmm.
This is a harder question than even I thought it was. And I went into this thinking, this is a hard question.
Mm-hmm.
So I'm going to try to simplify. And let's start with the basics of computing altogether. In standard or classical computing, I think everybody understands that when you boil it as far down as humanly possible, you get to a bit.
Mm-hmm.
And the bit has 2 states, 0 and 1. That's it.
Yep.
From that, we got YouTube. Okay.
All right. Impressive.
What we basically did, and again, simplifying, you combine enough of these single state holding units, and then you do a little electrical things to them, aka actions or logic gates or
operations.
Operations. There we go.
Hey, I'm here to help.
And you can represent anything you want, more or less, in the classical world.
Mm-hmm.
Using these computer things, you can model math, graphics, text, and even actually important stuff like podcasts and Xbox.
Yeah.
And all you need is billions upon billions of zeros and ones.
Yeah. And I'm sure you'll get to this later that there are severe limitations to what we can do with classical computing.
Yeah.
And specifically digital computing, which is what we're really talking about here, is representing everything in a digital format, zeros and ones. Because there was another branch of computing called analog computing that maybe we touched on previously and we should do a whole episode on.
Yeah, that's not a past tense. They still exist.
Yeah, and they are coming to the forefront for specific applications that don't do well in a digital world.
Right.
So, yeah, we're not going to, I don't want to go any deeper on that, but I just want to mention that digital computing is not the only form of computing, even going back a little bit. And quantum computing is not digital computing.
Right. Yeah, I mean, that's really the key to understand is that quantum completely revisits the fundamentals of how do we do things at the fundamental level in this type of computing.
Mm-hmm.
So in digital, which I'm going to refer to as classical just for simplicity's sake.
Fine, and that's what you wrote in the doc, so I get it.
You have either 0 or 1. In quantum, you have 0 or 1 or a superposition. AKA,
Right.
it could be 0 or 1, and we won't know until we observe it.
Right.
Now, what a qubit, which is the quantum version of a bit, get it? Quantum, bit, qubit.
You're very adorable.
I'll explain it on the whiteboard later.
Okay, excellent.
What a qubit stores is the probability of its value being 0 or 1 as a result of the application of whatever mathematical process we just applied to it. Right? So in classical computing, you apply some type of operation and you can just immediately know 0 or 1.
Right.
In quantum, you get it could probably be 0. It might potentially be 1. We'll figure it out.
Right. It's not a discrete value. It's
right. It's not even a value per se.
Mm-hmm.
0 is a firm number that is set in stone forever. The probability of this, it's so hard to say it without saying the word value. It's the potential of the state that is the key.
Okay.
And that's the key differentiator. And if you didn't think that was complicated enough, let me quote a little bit more depth about this from Microsoft's quantum computing group of all people. Quote, the state of a single qubit can be described by a two-dimensional column vector of unit norm. That is, the magnitude squared of its entries must sum to 1. This vector, called the quantum state vector, holds all the information needed to describe the 1-qubit quantum system, just as a single bit holds all of the information needed to describe the state of a binary variable. For the basics of vectors and matrices in quantum computing, see linear algebra for quantum computing and vectors and matrices, unquote.
Oh.
Now, I'm going to go ahead and stop right there
Right.
and ask you a question. Did you understand any of that?
Let's go with bits and pieces, but as a whole, no.
Okay. Before we go any further with quantum, I'm going to ask another question. How much about the ones and zeros above that we added up to make Xbox do you understand?
More than you might think.
You're such a liar.
Damn it.
You understand nothing.
Fine.
You don't even know where the sun goes when it gets dark outside.
The sun doesn't go anywhere. The earth moves, right? Right?
The point I'm trying to make is there's a lot of and then something happens in our understanding even of classical computing. And that's okay. That's fine. That doesn't mean really anything in terms of our intelligence or expertise. We are not that kind of computer scientists.
Mm-hmm.
So it makes sense that we kind of get it. But we really, if push came to shove and someone put, chalk in our hands and said, explain it on this chalkboard, we'd fall down pretty quickly. So it doesn't mean that we don't get quantum computing because we're in the same situation. And admittedly, the math in quantum computing is significantly harder.
Yeah. I may have mentioned on this podcast in prior days, I did start my college career in computer engineering. And somewhere around logic, gate, and circuit design, I ran away screaming.
Totally
And
fair.
yeah, that's getting down to that classical computing bits and bytes where you are actually figuring out how a logic system is going to arrive at a particular conclusion and how the actual like electric fields inside the transistors make that happen. And I couldn't do it.
Yeah.
So I was like, I thought we were going to be like programming video games.
Yeah.
We were not.
Turns out that's a different kind of computer science.
It sure is.
So anyway, when it comes to the very lowest level of how these things work, I really think in order to grasp the difference between classical and quantum, as laymen, we have to understand two things. One, the way that quantum does it is in fact infinitely more complex than how classical does it. And two, because of this, because the way of doing things is so unbelievably different, the way we get to the end result of quantum computing, aka tangible things that we understand at a fundamental level, like math, graphic, texts, podcasts, and Xbox, is going to be different.
Mm-hmm.
It's almost like writing poetry. If you are fluent in English, you're going to write poetry in one way. If you're fluent in Korean, you're going to write it in a very different way. If you try to map them one to one, you're not going to have a great time.
I totally get it. Okay.
So there will also be, because the fundamental approach is very, very different, there's going to be strengths and weaknesses. Classical computing is going to hold some sway basically forever just by the nature of the way it does things. Quantum computing is a little bit more of an unknown, but it's likely that there are going to be things that it absolutely crushes at and things that it struggles at.
Mm-hmm.
Right? So we're just in the process of figuring that part out. Now, admittedly, something else we have to remember, even if quantum did supplant in terms of what classical could do, that does not mean classical would go away. Because first of all, classical computing has a hell of a head start.
True. Yeah.
And if you've seen how the economy is unwilling to let go of obvious unnecessary things like fossil fuels, you'll know how difficult it is in this world to unseat the incumbent.
Yeah. I mean, classical computing is like, it's like a hammer and everything is a binary nail. Quantum computing is like an octopus.
And it isn't.
And it isn't. It's useful for some things. You can probably get it to do some stuff, but it's also weird and totally alien.
Right.
That worked out better than I thought it would.
No, you actually landed that plane. I'm shocked.
Yes.
You landed it upside down in a lake, but you landed it.
Any landing you can walk away from.
Or swim, if you're an octopus.
Another t-shirt.
Okay. So that's the background, and it's not really a background. It's just, that's what I think we have to have an understanding of to grasp where we're going here. Now on to the actual first point. Over the past bunch of years, and it's actually longer than the show has existed, quantum has existed, but it has evolved in terms of actual tangible results much more slowly than people thought it would. Okay. And I think there's a couple reasons for this. First one, it sounds real fun. Quantum computing has always been one of those things that people assume is right around the corner. Things are going to change overnight any day now.
Mm-hmm.
Just like cold fusion, right? People are still working on cold fusion. It always sounds like it's the next big thing.
Yep.
But in reality, in quantum computing, breakthroughs have been happening, but they've been slowing down dramatically, even as the technology that makes quantum computing possible continues to evolve. One of the biggest problems with quantum computing is how unbelievably fragile it is. Remember we said we had a huge head start with classical computing. Classical computing is also a lot more solid and robust. We can do classical computing just about anywhere.
Mm-hmm.
Voyager satellites are 11 billion miles away, and that's actually, at this point, not an exaggeration.
It's really not.
We have IoT that goes into volcanoes. Like, the different circumstances we can compute with classical computing with relative ease is staggering. The world of quantum computing requires perfect and consistent conditions in order to stop things from falling apart basically immediately.
Yeah.
And these types of conditions include things like near absolute zero temperatures. And this is a new one on me, no vibrations.
Not even good ones.
Yeah. And keeping things from falling apart gets exponentially harder as you add more qubits.
It's like building a house of cards, but like the cards are slippery and you're doing it on top of the hood of a running car.
I like it.
Okay.
So, what actually happens? So, this is a known thing in quantum science, not even just quantum computing. If you can't keep the environment that you're observing stable, you get what is called quantum decoherence. This is where a qubit loses its state. It doesn't like flip to a different value, it just doesn't have one anymore.
Right.
What I just described in classical computing happens constantly. A bit can, in fact, for a lot of reasons, randomly flip. But we have been editing this inconvenience out of the system for so long that people take it for granted that it's impossible. It's not impossible. It happens constantly, but we have error corrections.
Mm-hmm.
Ironically, as CPUs get smaller, this is actually becoming more of a problem because of the rules of quantum computing.
Right. Right. We're getting down to the 2 nanometer or smaller. And now we're talking about individual atoms.
Yep.
And atoms have feelings about things.
And they don't like to stay where they're put.
And they don't like to stay near each other either.
But that's a separate issue. In this case, with quantum computing, let's say you've got, I don't know, an operation that takes 15 qubits. If one of those qubits loses its state, it's game over. Right now, there's no error correction. You start from scratch again.
Mm.
So, especially if you're doing something complicated that takes a lot of steps, getting things to run absolutely perfectly from start to finish without any errors in between, big problem right now. So, with that in mind, it is no surprise that the number of functional qubits that we have in the computing world has stayed pretty low over the past decade or so. Over the past 7 years, I just want to give you a rundown of what were defined as the largest functioning quantum computer. 2016, 5 qubits. 2017, 14 qubits. 2018, 20. 2019, 53. 2020, 72. 2021, it's either 100 or 141. There's some complications about whether that was real.
Okay.
2022, 433 qubits. Spicy.
Ooh, yeah.
And in January of 2023, IBM's Condor quantum computer system announced 1,121 qubits.
That seems like a lot. I mean, compared to 5 only 7 years prior.
So, two things going on. One, going from 433 to 1,121 in effectively 1 year is a hell of a jump.
Yeah.
But here's the thing. Nothing of value has come out of it yet, aside from the fact that it has more qubits. Primarily for all the reasons I described above. Is this being done just as a vanity project or something that you can put on a poster? Maybe.
Yeah.
One thing we know for sure is that IBM has tacitly acknowledged that the legitimate operating size of 1,121 is not feasible for a while.
Okay.
They are basically stating that going forward, their plan is to build better qubits and better systems and better interconnects and all of that other stuff to link things together rather than continuing to develop larger and larger bulk systems that have more than 1,000 qubits in them. Why? Because these machines are so freaking noisy. And that's an actual quote. And what they're basically saying is there's too much noise. It's drowning out the system. We're not getting anything of value out of this 1,121 qubit system. It is just too unreliable.
Mm.
It looks cool. It looks like a modern work of art. There's a link in the show notes. It really does look nice. But to greatly simplify where we're at with the Condor system, imagine asking it a question like 1 plus 1, and it'll tell you 2. Great. Amazing. Fantastic. Now ask it 3 times 16, And it will tell you, like, blueberries. Or it will just not return an answer. And because of all the myriad things that go into why errors happen in quantum computing, we are not totally positive why. Another way to think about it, imagine a car with a liquid rocket-fueled engine. Sometimes it will get you to the ShopRite. Sometimes it will explode in your driveway.
Seems bad.
It is fascinating engineering that is simply not ready for prime time. Maybe I should have called it SpaceX.
But hey, be fair. SpaceX has made some cool stuff that actually works.
That's true.
Not sure I can say the same of IBM. Boom! Got him! Oh, it's not true either. I'm sorry. Sorry, IBM.
Every single thing that I have looked up comes back to the same problem. Errors in quantum are so prevalent and so hard to fix in flight that error correction, like we have in classical systems, is not even on the roadmap at IBM until 2029.
Wow.
You can look it up. They have a roadmap. Idealized systems from their perspective are still on the order of 100 qubits. So this goes back to that 100 versus 141. That was another IBM machine as well.
See.
I think it was called Eagle. I can't remember now. Or Egret.
It sounds like they are on a bird trip right now. Okay.
Their idealized system, when it comes to not the rocket ship in your driveway, but the Toyota Corolla, is 100 qubits and 3,000 quantum gates. Okay, now this deserves a tiny bit of communication, although we did kind of hint at what it is in the previous part. A gate just means a specific, repeatable, and in quantum's case, reversible state that is based on a stable quantum operation. So addition, subtraction, like, not like, etc., are all classical gates. In quantum, the gates are way more complicated.
Because of course they are.
The fact that all quantum gates are reversible is cool, but way outside my level of understanding. In fact, it's so far outside my level of understanding, I'm not even going to link you to anything because all of it just made my head hurt. Start with the Wikipedia if you're curious.
Fair. Okay.
So, where we are with quantum, everything is still promising, everything is still moving forward, but it's inching forward. And that's okay. We just have to recognize that it's not something that's going to revolutionize the universe tomorrow. All of this stuff is extremely skunkworks, and it's also extremely expensive because I don't know if you know this, but absolute zero is cold.
And hard to maintain.
Correct. As a matter of fact, if you read the IBM Condor article, they go into depth and not an unreasonable amount of pride, not just about the qubits, but about the cooling system.
Yeah, that seems to be pretty critical to the whole thing working at all.
Right. So I do not want you to be left thinking that everything is doom and gloom. Because point number 2, progress is being made. So remember, IBM's standard model is to approach a working system with a paltry 100 qubits. Well, that sounds pathetic, but that's because we're used to thinking of numbers in the classical model.
Right.
In quantum, they're very different.
Yeah, if I think of a classical computing model, we're talking about transistors that are listed in the millions, if not billions, per chip.
Yes. And the reason for that is you take a lot of ones or zeros, whatever that state is, that bit, and multiply it out with a ton more bits to make, bytes and then words and then actions and then functions and then things that we can actually understand.
Right.
But you need and I'm going to use a scientific term here, you need a buttload of bits to do it.
Exactly.
A quantum computer, because of the superpositions, doesn't work that way. It can hold way more data in state than a classical computer, which is another reason you can't compare them one to one. So for example, a quantum computer with just 20 working qubits holds 2 to the power of 20 states at once.
That's a lot.
And that's also not 100. You want to guess what the size of a working 100 qubit system can hold?
Is it 2 to the 100th?
Amazing work.
Look at me, I did it.
So that's a lot of data to process in one go. It's something that you would need what we call in classical a supercomputer to process. And that's one of the reasons, which we will get back to, that people are scared about this. But it's important to notice or to note that quantum can handle a massive amount of data at one time, even with a smaller number of qubits, right? Another thing to note is that this stuff is real in two separate ways. One, if you want to, you can write and work with quantum computers today. IBM, Microsoft, I can't remember if Azure has one. AWS has one now. There are cloud-based quantum computing services that exist that you can rent time on for a mere $97.50 per program execution. What does a program execution mean in this case?
Yeah.
I recommend you contact your salesperson and bring a fainting couch.
Ooh, it's a good thing I bought one at IKEA last week.
So these between 20 and 100 qubit size working functional computers are referred to in quantum computing as NISQ, N-I-S-Q, aka noisy intermediate scale quantum. The goal here is to get something small and usable, reliable, the Toyota Corolla.
Yeah.
And they exist. They're out there now. And real research is being done on them. And it is also progressing. The number one with a bullet, and the only one that I want to talk about today because of time constraints, quantum encryption. So first, the quantum encryption, classical encryption conundrum. Ooh, that was hard. Say that 5 times fast.
No, thank you.
So we talked about the amount of state that a quantum computer can handle. It can do a lot more work on very specialized tasks than a classical computer. Classical encryption is simply a problem that needs to be solved. I mean, literally, classical encryption is a math problem. I'm going to make a lot of math majors scream by saying this, but classical encryption is basically long division.
More or less.
Utilizing huge numbers.
Right.
So classical computing, because it is iterative, the only way to break classical encryption is brute force. 111, 1111. No? 111, 1112. No? 111, 1113. I could go on. That's how it's done.
More or less. Yeah.
I mean, there are other ways of shortcutting it, but that's basically the idea. And the idea behind making encryption more powerful is making that math problem so much larger that it takes longer and longer and longer to solve. Incidentally, this is another reason that having a long password is super important. The longer your password is, the more intricate that math becomes. And I forget what it is. I think if your password is 14 characters long with modern encryption, it would take like 1 billion years to crack.
I think it's even longer than that.
Whatever it is, it's way beyond anything that we are going to be able to handle with classical computing, at the very least in the next decade.
Right.
The problem is, what happens when quantum can handle all those states at once? The fear is it takes all that stuff in one go when you get to a point where it's workable with enough qubits. Remember the powers of 2 that we just talked about. And the fear is that quantum will be able to model that formula all at once and do the decryption instantly. Now, quantum encryption is intended to work differently. So first off, if we have quantum communication, quantum encryption is going to be unbreakable. And it's going to be unbreakable for a simple reason. It is a transient action. Decrypting will require a quantum action at the same time that it is encrypted on the other side. And if there is an outside observation of that quantum action, it will change the result and poof, the job will fail. Think about it like a telephone call. I call you on a dedicated line. The second someone tries to tap into that line, it short circuits and the call ends, right? Because it's been observed. Meaning 2 things. The 2 people on the ends of the legit call will have to reconnect, but the intruder will have gotten nothing. In classical encryption, you can say download an encrypted file or yank an encrypted disk drive, put it in isolation where it doesn't self-destruct, and you can bang away at it indefinitely.
Right.
Quantum computing is not going to allow that to happen, simply put. Now, I know what you're asking. Do we actually have proof that quantum computers can break classical encryption instantly, like the fear, uncertainty, and doubt that I just spread said it could? In the short term, the answer is actually no. It's been hypothesized. It has not been shown or proven. But in the future, the answer is still probably. With all the caveats in mind, it really is understandable that this hasn't been worked out yet. The biggest thing to get this to work is a system of the condor size, which is why I said in the future, the answer is probably. And that might make people feel comfortable, but I swear to God, it was 2 weeks ago that Jurassic Park came out. So time does have a way of flying.
Yeah. And I think what's interesting to remember is what you said, that because classical encryption, if you can pull that information and hold it in isolation, then you can decrypt it at some future point if you can break the encryption, which means that information transmitted today, if I can record it and it's still going to be useful to me in a decade, then when quantum computing reaches the point where it can decrypt that, anything that was encrypted with that algorithm is now going to be unsafe. Now, there's not a lot of things that a decade from now or 20 years from now are still going to be important. I mean, obviously, everything I've ever posted on LinkedIn is gold, but like most stuff is not going to be particularly important. But I'm sure there's some state secrets or some trade secrets or other really important information that will continue to be important a decade from now.
Right. Which, in terms of just our modern day today, is another really good reason to be as rigorous as possible and responsible as possible with the way that you handle your data, with keeping things encrypted at the highest possible level, putting in self-destructs, those types of things.
And there have been some quote unquote quantum safe encryption standards that have been established that in theory should defeat the quantum decryption or quantum attacks that have also only been theorized.
Right. And unfortunately, again, just because of the massive size of the data sets that we're talking about, the only way we're going to prove that is with a system that is much larger than a NISC, which we simply do not have right now.
Right.
Now, I actually had a lot more to say on this topic because once you go down this road, it does not take long for it to be 3 o'clock in the morning and you have 76 tabs open. Ask me how I know. But for the sake of time and sanity, I'm going to go ahead and stop right here. I had a bit on AI. I'm just going to go ahead and cut it. Long story short, think about it the same way we just talked about quantum encryption. There's a lot of possibility. There's a lot of hot air. Quantum is real. It has real world uses that can be tested even by yourself, even right now. More research comes out about different models, different theories, different hypotheses, literally every day. Quantum encryption probably deserves its own episode. And everything about AI, even in the quantum world, is overblown. Any questions? No? Fantastic.
All I'll say is that quantum, just the word sounds cool, probably because it starts with a Q, but also just quantum, like people like to add that to things, even things that have nothing to do with quantum, to make it cool. And there was that brief period of time where we didn't have a buzzword that we could apply to marketing materials to sell more crap. And so quantum kept popping up. Now we have AI. So that problem is solved for a while.
Right. And once we get to the point of having quantum renewable AI, then every single marketer on Earth is going to, have a dream come true.
Shut up and cut that. We need to trademark that right now. Hey, thanks for listening or something. I guess you found it worthwhile enough if you made it all the way to the end. So congratulations to you, friend. You accomplished something today and didn't.
Nice.
Rule of threes. We did it. You can go sit on the couch, play with a NISC, and explain to somebody else that that's not a dirty thing. You've heard it. You can find more about the show by visiting our LinkedIn page or check out the new website, pod.chaoslever.com. You'll find our show notes, blog posts, and general tomfoolery. We'll be back next week to see what fresh hell is upon us. Ta-ta for now.
I was so super proud of Microsoft. You go to their pricing page for quantum, and it is just as confusing and impossible to understand as all of their other pricing pages. It's just beautiful.
You got to appreciate the consistency.
And you don't.